Good morning, everyone. I am delighted to be the first of many people to introduce Eric Xing. I said the more important the person, the more introductions the person gets. And I happen to know Eric from many years ago when he was finishing up as a graduate student at Berkeley, and I was recruiting him to Carnegie Mellon. And I worked really hard to recruit Eric. He was very demanding. He was extremely demanding. Can I just say how demanding you were? He wanted, just to give you an idea, it was very typical for people coming to computer science at Carnegie Mellon to want an appointment in the computer science department, which I was the department head of at the time. And often these recruits would want a joint appointment between computer science and some other department in the School of Computer Science. Well, Eric wanted 3 appointments with 3 different departments. And he said, I'm not coming unless I have all 3 appointments. That was how demanding Eric was. And I got him those 3 appointments. He was unique in that way. And I also wanted to share 2 other personal stories with her. I have watched Eric grow up professionally all these years. And I remember once I had my usual one-on-one with the faculty in the department, and I had I went to Eric's office, and he served me this fancy espresso in this fancy, remember that? Like it was a Nespresso machine, and he didn't have just he had this array of colorful pods. Like, I don't know, just give me one. So anyway, I realized he had fine taste, exquisite taste in coffee. Now, moving many years, I visited you at Facebook, I think, and all sorts of things. I watched Eric grow up. But the most recent visit, he came to visit me at Columbia in my office at Lowe. I don't know if you remember this, Eric. Do you remember? He had these blue suede shoes on. Do you remember that, Eric? Well, I thought, again, exquisite taste in fashion. So I am now trying to embarrass Eric. But he is a phenomenal researcher in AI. And I can't speak more highly of him as someone who has moved the field in so many ways. And now I'll pass the mic to Tian? Vishal? Okay, Vishal. Thank you for coming.
Well, thank you for that introduction, Jeanette. So, this is continuing in the distinguished lecture in AI series that we have at Columbia University. This is the last lecture of the series for this academic year, and we're ending with a bang. The last lecture was from Jan Stoica, who got his PhD at CMU and became a faculty at Berkeley. Eric has taken the reverse path, but has, of course, gone on to do many, many wonderful things. So, to introduce Eric, without talking about his taste in coffee and shoes, I invite Tian Zhang, who's the chair of the statistics department at Columbia. Yeah.
Okay, so I'm here to officially introduce our speaker today. It's my honor and pleasure to introduce what I regard as my friend and my colleague in machine learning, data science, AI, whatever the name you define this field we're both working. So before I read out a short version of your very long list of achievements and current vision, I just want to say one thing. The reason why I feel very especially connected with Eric is that we met at a statistic conference. And then I think one of the appointments Jeanette successfully secured was with a department of statistics, I assume. Machine learning, statistics, and computer science. Yeah.
unfortunately, Steve Bamberg told me.
So currently with all the AI research is become, ever more important for all the fields to come together to work on important problem together. And Eric has been a strong voice in this effort, trying to bring fields together. So that's why I feel especially proud to be able to, be part of the effort of bring Eric here today to, share his vision with us. So as you have read from his bio, he's the inaugural president of MBZ University of Artificial Intelligence, a fast rising global leader in AI research. And I don't have to read all the university achievements over the past few years, rising in ranking, in many ways. So Eric's vision for the university is to think out of the box, to really, at a new university, they were able to quickly launch research education effort using innovative models. And Eric also has a vision of how AI research could be quickly integrated in a lot of important areas affecting our society and people's life, from health to language to technology to climate. And so I'm super excited about what he is here to tell us, and the floor is yours.
Thank you very much. Just sound test. Can you all hear me clearly? Well, thank you very much. I'm so grateful for such a reception. I'm very, very happy to see Jeanette, who have been my mentor, since I started my career at Carnegie Mellon, and of course, Nisha and Tian, long-term colleagues and friends. There has been a lot going on these days in AI and machine learning. And one of the major, frontier area is about how to do reasoning, the way we do it, or maybe the way better than we do it. So my talk will be focusing on some of my recent work with my colleagues at Carnegie Mellon, at NBZI, along that track. This talk was freshly baked until last night, so bear with me if you see something that is kind of bumpy. It's going to be a difficult talk. It has 80 pages, equations, models, algorithms, results, and so forth. It's a technical talk. So I hope I can sell you, and advocate to you, what I see to be, a proper vision, to move forward along this line. It's so exciting to present this talk, as a closure of this series, and also in front of my old mentor, Jeanette. In fact, I also see Yun, who used to be sitting in my class in graphic model. It's such a nice reunion of, all the friends in the past. So, yeah, so there are a lot of advancements in AI as we all see it. Large language models, autoregressive, transformer models, have been used widely across the spectrum, in natural language processing, QA, in visual and image applications, and even in science. They all built on somewhat similar fundamental architectures, which we call a transformer, and some attention mechanisms. There has been a lot of debates, in fact, these days, whether such a technical roadmap will lead us to, say, AGI, right? So there are a lot of debates. Many of you probably saw one school of opinion like this, which was championed by people like Sam Altman, people in the industry. They believe that we already find our way toward AGI, and we are at certain initial levels, such as a good chatbot, maybe already entering level 2 as a reasonable reasoner to do human level problem solving, and we are heading toward agent systems, that can take actions, and then the next will be turning them into innovators, to really help us to do science even better, and maybe even collaborate to form organizations, by those agents and so forth. And there's a hidden level that he didn't say, which is to take over civilization. Who knows? And obviously, there are objections to that view. For example, my friend Yang LeCun, has been a strong opponent of that kind of school that relies on large language models. In fact, he particularly didn't agree the religion on autoregressive large language models for all those. And he make a few points, technical deficiencies of those approach, such as lacking the long, term memory and not having, the persistent memory and the reasoning planning capability, not having the understanding of physical world and so forth, right? So, okay, that's great. So I don't have to prepare all of you. In fact, later in the talk, I will see a point-to-point rebuttal of some of the things that he said. So it'd be interesting to hear your response as well. Of course, there's someone who sits in the middle. Right. So I think this conversation is interesting, but somewhat misguided because it's all focusing on intelligence, which in my opinion is quite a subjective kind of a description of a state of the being. For example, some musicians may play very, very good music, and you probably cannot match him, on that capability. But maybe you present him a math problem, he doesn't have really a good sense about that. Do we call him not intelligent? Well, that's not right? So in a sense, I would imagine that another way of defining intelligence maybe is in terms of problem-solving skills, capabilities, and the values out of it. And that actually, is, able to, turn even the design and also the discussion about our current AI technology in a very different way. And this is basic direction I'm trying to explore in the rest of the talk, which is focusing on capability and utility. And then based on that, you can probably make your extrapolation on whether agency, free will, and so on and so forth, which are spiritual and philosophical, can actually happen after that. Again, why we need capability? Because we need to address needs. And there are a lot of human needs, as Maslow put on this pyramid. And you can literally just build a pyramid of capabilities from preliminary fundamental to very, very advanced and high level. For example, we want to have the ability to read, right? And to write and to do logic and reasoning and plan and so on and so forth. And then the task can be designed accordingly to validate and qualify such capability. That's usually, what we do, when we enter an interview and when we will test it, for our skill and so on and so forth. And in that sense, you can now place what we have now in the model space, in the system space, to this ladder. For example, I would clearly place LLMs, large language models, probably in here. They can now read very well. They can also write quite well. I noticed that nowadays many of the, professors even, not alone, politicians, are using ChatGPT to write their speech. I started at least looking at those materials. I was actually quite surprised and in fact satisfied. I once asked Google, the OpenAI deep reasoner to write a summary of my own research. I think they did a little bit better than my students writing, right? So it's pretty good. And if you go all the way top into like a prophecy in the future, maybe you need a crystal ball. But what's to develop in the middle to answer those questions, reasoning, planning, right? Is that going to be another LLM or something else? Well, let's look at along this direction, what LLM actually can do. Well, LLM is built to do one thing. Technically, they are making to do next word prediction, right? And you can argue, whether this system understand what they are talking about and so on and so forth. But that's not the point. The point that somewhat through the next word prediction, they can engage you with a very high quality question answering sessions. They can solve your problems and they can maybe, help you to write to the point that you may want to, disregard even your concern about whether they understand the word and so forth, because that may not be, what you are looking for if you only care about the outcome. Likewise, in video models, it is doing next frame prediction and the generation, right? And the people argue that it's just pixel manipulation. They don't understand what they generate. But, if I'm going to a theater and watch a movie, all I care is that I have a good visual experience. I really don't care, how those pictures were produced. So in that sense, you can kind of remove yourself from that philosophical controversy and debate about what is making that whole thing work as long as it is working. I think the the new trend, at least in industrial AI, is favoring that approach, focus on the productivity and the outcome, and maybe go back to answering why that happens later, right? So that's kind of what I see happening now. It doesn't matter, in many cases. And in fact, I think this attitude, maybe this viewpoint, somewhat was actually echoed, at least subconsciously already in the scientific domain. For example, this famous statistician George Box once said, there are no right models, but there are models who are working, right? So LLM, in that sense, is working. But then you can also, push the point back and say, where it is not working, maybe that's where I need to, either find out why it isn't working, or maybe build something that's actually working instead. For example, here are some examples about the current limitation of LLM. I don't call them unintelligent, but I can, confidently say that they do not work, in these particular problems. For example, language is probably not always the effective way of describing the world or describing everything, right? For example, we have, fluid dynamic equations, for the water. But, if you ask the LM to tell you how to pour a glass of water without spilling out, you probably won't have a very satisfactory answer. But even an illiterate who didn't speak a thing about physics can actually do it perfectly. In traffic control, same thing. When you drive, I don't think you are doing wordy and, linguistic reasoning, right? In fact, you don't even do pixel reasoning because you don't actually see all the pixels. All you see are floating kind of, blocks of concepts and, colors and everything, that kind of inform you, how to steer your wheel and so forth. In a sense, that reasoning is not very, very complete, but it's adequate, without using language. There are also spaces where it's not even contained in language. For example, how do you learn to swim? How do you learn how to do rock climbing? These days become my hobby. Reading a book isn't enough. You never learn how to swim by reading a book. You have to basically jump into the water and rely on your embodied experience to feel the flow, to feel the touch and everything, right? And I'm not talking about even like a moonwalk to the moon. You never go there to practice your walk. You have to basically practice in here, in a different environment and then extrapolate to there. So that's where I think you see the limitation of large language models, but also you see the way of gauging any existing models in terms of their capability and then find out how to extrapolate beyond that. So this is how I, see to be useful to extrapolate. First of all, let's define the space of reasoning, right? So LLM lives in this space. It's about lingual intelligence, and through lingual reasoning, I would predict that anything, that ever can be written, described in language, you can imagine that eventually they will be all, taken care of, and satisfactorily answered, by a large language model. That's actually happening. Why, for example, a LLM can answer, Olympic mathematical problems, very tricky problems, because those theorems and those materials are written in text already. And therefore, imagine, a system that reads all the text ever written in human civilization, and then they read it very well and remember all the things and also all the next token and the missing token predictions. I wouldn't be surprised that just somehow they can find out a way to answer your very difficult math problem, right? But I can easily, just beat the system by not asking a more difficult question, but just by extrapolating the space. I will move beyond language and go into spatial and time kind of space where you have visual, you have audio, you have sensory and multimodality information. And that's probably Yann LeCun's view. A cat, maybe is smarter than your LLM because it is living in a different space. You can also make it even bigger by adding, agent, multi-agency into the whole thing so that you start to see adversaries, you start to see manipulations and purposeful actions and so forth. And some may be, okay to be dealt with by language, but maybe there are something else beyond language, depending on physical environment and situations. And then, of course, ultimately, you may even go to the world of nature where science, physics, biology pose more challenges and new data, right? So that's basically where you see the increased complexity form of reasoning. And I think it's probably now become a little bit easier to appreciate that why large language model isn't getting us to super intelligence, because you have all such spaces which is beyond what language is able to cover. So what a super intelligence and what a super capability look like? Let's maybe imagine maybe the ultimate intelligence that could have been made, and then let's see how far we are there. Right? So I happen to like this scientific sci-fi classic called Dune. I don't know whether any of you have heard about that. It's a very, very classical reading, which inspired like Star Wars and many other movies and productions. Right? So Dune is about an individual called Kwisatz Haderach. He is such a superhuman, which has this super intelligence, in the sense that he can command, for example, an army to win a galactic war, in the galactic space. He could also conduct or steer, as the so-called global scale project, turn desert into greenlands, into paradise, and so forth. And the way he does it is because he has the ability to inherit all the experiences and memories and knowledges from his ancestors. And then he could mentally simulate all possible plans that is needed to solve a problem and form his very vast mental experiments and simulation. In fact, there is even a way to mathematically describe a behavior, in the sense that the more memory, the more ancestry that you are able to inherit, then the more thought experiment you can do, and then the more intelligent you become. So sounds like actually a plausible story, in fact, to build an artificial system. Although the height that is described here maybe is beyond what our current technology is doing. But I want to use this maybe a way of thinking to try, propose, maybe a legitimate, viable engineering roadmap. Yeah, as I said, such a superhuman may be not possible with current technology, but I think we can probably try to build a system in that way, with similar functions, just focusing on all these capabilities step by step. So that leads to basically a more like a goal-oriented agent acting in the environment and then achieving the goal in a DOM fashion, right? So I have a few keywords in here. You have an agent that's now goal-oriented. It's to be anchored on here, not to say an agent that is intelligent. It is literally aiming toward a goal. And then, you are given an environment, which gives you the scope of the information that you are able to receive and also you are able to act on. And then the DOM fashion is by simulation and by mental experimentations, right? So that's basically going to be giving you the rest of the technical materials that I'm going to present. So I will start with what such an agent may look like in the optimal sense, right? So this is what I kind of took from a classical textbook, reinforcement learning, and blow up a little bit, to come up with maybe a ideal design of a agent, right? The agent lives in a universe. The universe has the states, which are random variables, that you may imagine in perception or in observation. And then the agent will, conditioning on, the world states, propose actions. Action, acts on the universe and generate the next word and so on and so forth. And eventually they drive toward the goal. And then, of course, there are critics to help you evaluating how far you are away from the goal and so on and so forth. So these are pretty much a kind of a fancier version of a classical reinforced learning system. The problem is that, of course, it gives you the mathematical context about how to, define, a function that can maximize the expected chance of success, which is on the right, on the left. And then that also results in a decision rule that optimize, such outcomes. The problem is that it is not practical because, say, I cannot use this agent to tell me or to, instruct, my astronaut how to do moon work because I don't have the moon here yet, right? So that's actually bring naturally, a model-based approach. How about we put a model called the word model, which could simulate the world states. And the relationship between the world states is that it is giving you, a virtual environment where your action, again, simulational, can be dependent on to propose the next actions. And then the universe also, gets a more careful and realistic treatment because the real world states were never observable. You don't actually know what God is thinking and what nature is acting, but you have observations. And the observations can be actually distilled into your belief, right? In nowadays, we call them encoders. But, we human brain, our sensory is an encoder, of the sensory information into your brain. So your belief basically can be, used to trigger, for example, a simulation in the world model. And then you can now do these mental experiments. And then hopefully your goal variable, your critic function can be applied, to those virtual states. Okay. So that's kind of lay out the technical roadmap about building, a goal-oriented agent. And in here, the advantage of having a world model is that you can now do simulational reasoning without going to the physical world. And in the next couple of minutes, I'm going to now present you how such a world model and agent models can be built. And I'm trying to ground the conversation as much as possible to what we came from and also what we are using now, and hopefully to draw a connection about, how such a idea is more than just an idea. It's actually, implantable and also can be tested. For example, when we take a transformer-based word model, a large language model is to next word prediction, you can imagine the core function of the word model to be a next word prediction. Of course, for certain purposes, as I'm going to tell you. Why we need the next word prediction? I think I said that already, but it's actually maybe better appreciated if I give you, maybe a physical example. Because in machine learning, in AI, people are obsessed with optimization, right? If we know the goal, if I have the condition, the sensible thing I do as my statistician, as an engineer, is to optimize toward the goal, right? So that's kind of a very, very mechanical way of thinking, and it's very effective. But we human beings don't do that all the time. For example, let's imagine this situation. You see your friend, shedding tears, and you ask, how can I help? Well, if you ask a system, maybe the system will hand you a handkerchief and wipe your tear, or say something nice. It's a very direct kind of a linear, autoregressive reasoning. You autoregress from the target back to what you have in your hand as the tool. Right? But I think a real human being would be a lot more empathetic and sensitive. She probably can make some small, mental experiment using her internal word model. Say, maybe if I do something, this person will be stop crying, which is quite nice. Maybe I will be very tired, after I do so because she is really in a very bad mood. And maybe even after I do what I need to do, she couldn't stop crying. Then why I do that, right? But the third option could be whatever I do, she may be very grateful, even if she couldn't stop crying. So these are possible outcomes depending on what you can do. And you do that in your brain. You didn't do that, in real physical world because you have just one chance when you actually unleash your actions, right? So this is a common sense behavior of individual. But how to build a system with that behavior? So that's where a word model kicks in, because the word model can help you to generate all possibilities. It's a generative model of possibilities. Okay. Not actually a generative model of images or text. Okay. The possibilities can be concrete and can be abstract. The most important thing that you can have action onto it or simulative action onto it. So here are examples of what are those possibilities. They could be physical and mechanical phenomenon in the real world, like the water flowing, throwing an object and so forth. It could be also embodied experiences, your touch, of an object, your temperature feeling. For example, when you hand you a glass of water, it's hot to someone, but it's maybe not so hot for someone else. All these nuances are not necessarily, easily describable in an image or in a text domain. It's a sensory experience. Also, it could include emotional experiences, and mental experiences. And, in fact, counterfactual what is another thing. This is a what if question, which actually never likely to happen in real world, but you want to be prepared, is a pure hypothetical phenomenon. And you need to have a world model to simulate that. Otherwise, your autoregressive engine isn't going to get you, to that conclusion or get you prepared for that outcomes. In fact, our very biology evolution is also maybe an outcome of the world model in God's hand, because the God is not making you to be perfect. Okay, it's not like I want you to be standing and looking far and jump at a certain speed. That's not the way, any biological creature, is created, right? It's real. What's happening in the natural world is through random mutation, and then some become fit in a particular environment and they survive. And some may be unfit here, but elsewhere they may be actually fitter. So this is again an experiment. So there was school in philosophy describing this way of reasoning called hypothetical thinking, right? It's not about induction and deduction. It's really about the thought experiment. And imagine, a thought experiment under a world model. So here is a more mathematical definition of the world model, which is, if you are a statistician, you could call them a conditional distribution of the next state, given the previous state and the action you act on. And this function is magical and very powerful if you can make it very rich and correct, because then the bot, can do the following. With the goal, he could now start to simulate multiple trajectories or plans toward that. And then once you have a sensible critique function, which actually could be modularized in a different, implementation or artifact, you can start to choose the plan, right? And you execute one of them. And that's actually what's actually driving some of the earlier breakthrough, in modern AI systems, such as the AlphaGo. AlphaGo is actually literally, a simulative reasoner, which basically simulates all different board moves, toward a goal, which maybe increase your area or to be defined, in a particular setting. And then you have a search algorithm in here, a Monte Carlo tree search, to just compare all different options and then make one. And then the power of the system become very clear, which is how many steps, how far you can simulate, right? How many states you can cover and so forth. Now you imagine that, you replace this very, very simplistic board configuration, which is the word, in fact, of this Go word model, to be a fancier word model. For example, the word model of city traffic. Then, you can imagine that what's being simulated are different situations of your driving behaviors and also environment and outcomes. You can also now start replacing the word with other environments. For example, a battleground scenario, you can put, all the, tactical, and the weaponry, contents, into the situation. And then you suddenly become a strategist, maybe commanding, battles and the operations, right? It's becoming more interesting when you talk about, how can we go to the Mars and how can we walk on Moon, because, you never want to just go there first and start planning. You have to basically rely on your simulator to plan as much as you can, and then have, a good amount of option, in your strategy and plan before you even go there. And that's actually where, the world model become particularly important and interesting. And it's very important that the world model allows you to now, transfer knowledge. In fact, people are subconsciously doing that in the past already. We just don't call it a world model. Your flight simulator is a world model. Okay. You don't go to the aircraft to fly, but you are in the simulator, which actually just simulate all possible, outcomes and of your flight experiences. And the more you simulate, the better, right? And, I can actually teach you also something, not necessarily direct. For example, I can teach you how to do mountaineering. I'm sure that, when I send you to the mountain, you can automatically transfer those experiences to be, a combat, individual or a settler in the mountain, just because the skill, are very, very transferable, right? So that's, how a world model, we should expect from a world model. now the question comes down to how we build it. But it's important that we know what we expect, and then you can now qualify whether the model is adequate or not. And I hope you appreciate that I didn't use a single term, time of intelligence. These are all very, very, mechanical and numerical and also quantifiable, right? So this is a proposal of a new world model architecture, which I call the PAM model, physical, agentic, and nested, and you will see why it is called that way. So coming back to our world model, kind of the agent model, bigger architecture, now we're going to focus on this part. I think the key component is to really figure out what's the right representation of the information, what is the right architecture to allow information flow and integration within the model, what's the objective function so that you can train it based on, hopefully unlabeled data, and then how to use it. Again, there are a lot of proposals these days. Everybody call them are working on a world model, and here are some prominent examples. I'm not going to spend time describing all that. I think you are all very familiar with all those, but you probably can see that the way to demonstrate all these so-called world models, almost without exception, is to play you a movie and also maybe show you a few pictures, right? Which is problematic because if your focus is really on video generation, you tend to be carried away focusing on the visual effects, the nuances of the pixel quality, the sensational pleasure, and so forth. But why you need such a model? It's not to produce movies. It is for you to do reasoning, right? So in that sense, that kind of video generator isn't necessarily, leading to, the ability of actionable modeling of the real world. And there are some more recent proposals, including what I listed here, which you probably heard very frequently. These are very thoughtful and vocal schools of thoughts regarding the world models, right? And I will read a few opinions that you probably are very familiar and are probably working on, and I will maybe share with you some of my critiques on why some make sense, some may not, and then what is the solution to that. For example, there has been a strong advocate against using language to train world model because, it is just, the data is not big enough. Maybe you already exhaust data. We need to look into video data, right? So that's one school. There is also, a suggestion that, the representation of world states should be a continuous embedding instead of a discrete one, because on continuous embedding, you can apply gradient descents to do faster inference and so forth. There is also, a strong objection of using the autoregressive generative model, and because they are doomed due to cumulative error and also some of the deficiencies of autoregressive design, in the learning. Also, there has been objection on using probabilistic reconstructional kind of loss function to train because it's intractable computationally and sometimes may lead to a very, very strange behavior, such as capturing not able to capture variations of the outcomes and so forth. And then of course how to use it. There are debates about whether you use reinforcement learning, or you do more like a direct model predictive controls. As a result of all these proposals and ideas, there has been, a architecture floating around, which looks like this, right? You started from your observation, and there's an encoder turning them into latent states, and that's where your word model is plugged in, and then they deterministically predict the next word, and then very, very interestingly, with a fixed embedding of continuous, vectors, and with deterministic of embedding predictions, how to qualify? Well, it is to actually go close the loop this way. You go to the next sensory. You also use an encoder to generate a latent states, and then you measure the differences of these two latent embeddings. So it's to minimize the latent reconstruction error. Okay. So now I want to share some of the maybe I'll walk you through some of the details in the ideas behind this design and see whether it makes sense or not. So just to recap the bigger picture, we have a external environment where we get a signal from. we want to have a word model, which is maybe our mental model of the reality, which can respond to this external signal with, a proper representation first, so that my hypothetical thinking, my simulation could take place in what we call maybe a thought space, not in the physical space. And then as a result, I'm going to turn back an action, and then I'm going to hopefully implement such that they are working in real time, doing simulational, simultaneous reasoning. The key considerator here is about data representation, model loss, and usage, which I just, flashed at you some proposals in the literature already. So what goes wrong with each of these proposals? Data, right? So there is this very famous statement that LLM, isn't really using big enough data. For example, there was an example on how much data even a 4-year-old child can perceive, until 4 years old, measured by the data volume in terms of pixels, in terms of bits, right? You see a lot more information indeed, than all the text people could use to train large language model. It's a very strange argument, which appears to be very convincing, because indeed, babies, saw more data measured in that way than even a large language model. But why we still need to enter graduate school and high school and read? Why we turn someone from illiterate to literate? Because language is a high density information. It's not just information. The information has a density and has a quality. Okay, the information content over there is different. It's not just about the volume. So I think I don't need to say too much to convince everyone that maybe language model or language still is a very, very useful, maybe the most useful information, but you need more. That's all great. So I think the word model need to embrace multimodality and having this mixture of information. So that's kind of my first response to the suggestion. The second one, representation, is a little bit tricky because it is taking into consideration about the actual computation needed to make the model work. And the proposal is that you want to have a continuous representation, which is friendly to gradient operations. However, continuous representations is a very unstable representation. In fact, now I stand here, I watch you, and I move to here, I watch you. I will result in two different representations, which is not clear whether they will lead me to the same answer if I have a word model. Okay, so this variability, this noise, needs to be taken care of if you use a continuous representation, of course, in return for a computability. And the human doesn't do that. In fact, the human being is very good at tokenizing and discretizing real-world information. That's actually how language is invented. Okay, we don't actually communicate using gestures all the time. We actually use language. And language is a very, very condensed form of information, which is what I call a human token of a real world. It would be bizarre if we don't use that and try to relearn everything just from visual. Right? And also, large language model is an excellent technology which allow you to do very, very strong reasoning already in the language space, right? And nowadays, people have invented techniques like VQVAE, which can actually tokenize, the real signal into discrete form by paying some cost of computing. So the issue is really about whether are they good enough, or you want to remain in the continuous representation space to do the more authentic, lossless kind of information processing. I think the experiment we see so far suggests that, say for example, this is the input video, as in here, and this is what we show to be the continuous embedding, in fact, from a joint embedding technique advocated in those schools. It's hard to actually, distill any semantic meanings from this embedding, to be honest. And you may, run into, this convergence issue, or maybe this deterministability issue, in your computation. So our proposal is to really use a mixed representation, where you continue to use discrete tokens whenever you can. But if there are really something, that is beyond, a word, for example, or you really need a very, very fast reaction, which sometimes have this sub-instinct kind of reaction. When you play the piano, sometimes you don't read the score. It's muscle memory. Okay. Those kind of behaviors may be okay to use a continuous embedding, but how about we allow both to happen? There's also a theorem, which is very interesting. In theory, any real world signal sequences can actually be captured with a bounded loss, using, a tokenization scheme or finding a language expression that is built on this token. I think this is a very important insight because it gives you a direct way of making trade-off between your memory and between of your computing. And I want to show the theory a little bit. So these are basically two ways of dealing with this part, the embedding in a discrete space. One is to scale up, build a larger vocabulary. In fact, that's our earlier phase of school learning. We actually build vocabularies, by just remembering all the words, even though we don't have ability to speak complex languages. But if you become adult, you really master the way of using these languages. People choose to, scale out and, write long sentences. Like I was often criticized for my paper having awkward long sentences. That's a defect, due to that kind of behavior. But there is a way to mathematically understand the trade-off. It turns out that for any continuous sensory reading of the data that are, somewhat apart from each other, however small they are, you can always, come up with a language, which is by a set of discrete tokens and also a language expression, which is a sequence of these tokens to tell them apart. It's a very, very, assuring guarantee mathematically that this technology is actually not causing you to severely lose information in reasoning. And at the end of the day, it's becoming a computational trade-off. You have an exponentially growing cost of building the vocabulary, and you have a logarithmic complexity in growth of the coding length. And you can decide by yourself which one you want to go. So my conclusion is that the representation in the discrete space is likely to be working. And especially when you are willing to use a mixed coding, then, you are hopefully not, losing too much to a pure continuous embedding. Now, architecture is another issue that has been debated very heavily because, yes, this autoregressive learning idea, appear to be very stupid, very mechanical, not very sensible. We already have an example in the past, right? But, do we have alternative? That's the question, right? It sounds like people believe there are alternatives. For example, in this JEPA, setup, instead of doing autoregression over two observations, I'm now defining the loss over two latent embeddings. Well, I have to say that mathematically, I still think it is autoregression. It is just an autoregression in a different space. If you look at the equations, right, we turn next observation prediction into next represented predictions. So by definition, it is autoregression, even though the loss function for the latter, for this one, missed a few terms, which includes the encoding cost. So that's basically maybe a way to compromise, that contradiction. Yes. Oh, JEPA. It's called joint embedding and probabilistic. I forgot about that, but just take it as a name, basically. What I gave you already, the definition is the action part. Joint embed, JEPA means that you just find these two continuous representations jointly by minimizing these loss functions. Okay. So what we would propose is to actually use a generative model, built on a encoding and a decoding scheme, where you can actually, try to, leverage on the so-called reconstruction error, in the observation space. And you leverage on also the ability of something called a hierarchical encoding scheme, where you rely on diffusion models to, to capture low-level perceptions. And then you use the language backbone to do higher-level word dynamics. And then your source space hopefully can handle even higher-level reasonings and so forth. And that's basically allowing you to leverage on existing strengths in language model, but without losing, the ability to process continuous information. Another issue, of course, you've already raised, JEPA, is, offering, somewhat a difficult way of training, because in here, we are no longer, observing or measuring a loss that is visual and sensible, to your measurement, because they are all in the latent space. And mathematically, people work in the space of statistics, should probably be familiar with that. If you define your loss function purely based on latent variables, you can kind of guess it's going to run into a number of mathematical numerical issues. They either are degenerating or they are divergent. And therefore, to make this model work, people used tricks like regularizers and so forth, which actually add back the complexity because you design them right. And also, there are even additional technical, open questions, which I'm going to lay out in a second. But what if we just go back to our generative loss, where you define your loss function, over the differences of your reconstruction of the next observation versus the actual observations that you receive. It kind of makes sense. The question is that how far this and this are away from each other, right? If you can convince people that after all they are the same thing with a different degree of qualification and actionability, maybe this become more receptive, because it is autoregression. It makes you less kind of excited because you are using kind of existing old school ideas. It turns out that this loss function defines an upper bound of this loss. You can prove it mathematically, which actually also exposes a flaw of this loss, because if this loss, the latent loss, is a lower bound of the generation loss, and then you minimize a lower bound, what do you get? You fail to basically improve the quality of the learned model, because you can always move down the lower bound without changing the actual curve you want to optimize. That's actually a mathematical degeneracy problem, which also can be studied through a few theorems. I just want to highlight the gist of that. Basically, you can always find a cheat configuration or a dummy situation where you minimize the loss of the latent reconstruction without even learning anything from the data. That's possible. On the other hand, if you minimize that reconstruction loss, you can always go below whatever can be achieved by minimizing the latent loss. So theoretically, it makes more sense to actually minimize a generative loss, even though it is meaning autoregression. Last but not least, in using the word model, there has been also some proposals. One prominent one being, the model predictive control, which also makes sense. You want to choose such an action which go directly optimizing, your fitness to the goal. Okay, optimization thinking. The problem is that it is very difficult to achieve, especially if you are very far away from the objective, right? So alternatively, you could imagine, using a reinforcement learning to start, using the word model in a different way. You simulate multiple strategies. And also you can distill from the word model simulative experiences and train the agent model using reinforcement learning. It offers more flexibility. It's more costly, but on the other hand, it is a lot more flexible. So this is just a quick wrap up of some critiques of existing schools of thoughts, which leads us to a new design, which is summarized here. So here the gist is that we need a word model which can handle both continuous and discrete information. And here we use two backbones. One is more based on it's a sensory decoder based on a diffusion model that gives you the ability to process sensory data directly, and hopefully gives you that kind of reconstructability of perceptual experiences for interpretability, and also act fast. You can then go one level down to turn them into discrete representations if needed, and use what we call a word model backbone, which is enhanced from a pre-trained large language model, which is beyond, in fact, the data that we could collect, in the visual space in terms of the information content to support reasoning at that level. And that also allows you to, encode simulated action, by not just sensory data, but also you can steer the model using words, which is also quite interesting because, it gives you maneuverability and the instructability of the models. How to train that? Well, you can actually now, define, very, very, straightforward reconstruction laws on the observations. And we're hoping that such a model can, generate you experiences, across the domain and very general and also very actionable and manipulable. So here I'm going to show you a few examples. So this is, a model we actually, built, in a world model, one single world model, and look at, the behavior of such a model. One thing that is very important for a world model to be useful is that, you can ask the model to generate what you want. So for example, we started from a current state and say, I want to, move forward. Okay, that's actually moving forward. But, I could also ask, the system to go up, lift up, which is not ever seen in your car. Maybe you are in an elevator or in a helicopter, and you can also do something differently. Right? So this manipulability, gives you at least actionable usability of the world model to simulate multiple environment and behaviors. Whether it is intelligent, it is knowing what it is doing, it's secondary because all I care is that it is able to follow my instructions. You will see more examples like here, very, very, diverse, real or even serial kind of a word and agent behaviors, such as, I think driving, from a first person perspective, from third person perspective, a indoor drone and a outdoor drone, robotic actions, in different, situations and so forth. So that's another kind of, dimension that you can see how word model, can, imagine, or simulate different scenarios. One thing I want to point out, you don't want to compare this to a Sora, which gives you that fancy women walking on Tokyo Street. That's a very high quality video. But why I need a high quality video if my goal is to make decisions, right? So that's actually the very, very interesting point. Here, I only need the quality good enough for me to make decisions. And here, it's really about demo. I don't even need to demonstrate that when I actually make decisions. That image generation part is actually not very important, to be honest, for the model itself. That's why I think calling the word model a video generator is very, very misleading. There are more options. For example, you can really steer the engine to go into both real and the imaginary world. In here on the left panel, I have, the time points where I actually typed in some actions and you can see what's happening. Right? You enter the door and the snow world. And, it's a bit bizarre, but then I say, how about, I go out of that door and go into a rainforest. So you can see the smooth transition, between alternative words, but at your request. And you can then put action on that and hopefully experiment with that action to see a consequence. And then you unroll back and say, oh, I really don't want to go to that volcano. I want to go somewhere else and so forth. So that's kind of how word model could work. You can also use that to now really design a game because game is really about, in a virtual environment, with fancy controllability, of all sorts of things. And in the past, we programmed game by a long list of if-else instructions. Okay, it's predetermined, pre-wired for actions. And here it is literally, simulated based on your instructions. We have some other videos which plays you hours-long movies and so forth, which is very different from the current video generator, which gives you 1 minute. Why 1 minute? Exactly because there isn't an internal word which helps you to keep track of consistency over a long time span. And that's why, the video after you watch long enough fall apart. It's a pure pixel manipulation. And in here, you have the word state, which actually keeps continuity of the word status. And that's actually the trick of maintaining continuity. So there are some applications I just want to highlight here, which helps you to solve a wide range of real tasks, which I don't have time to go into detail. Alternatively, if you, rely on what I just criticized about, those JAPR models and so forth, unfortunately, they only are able to right now handle some rather toyish situations, which actually has been solved many years ago through other algorithms already. Because, you have to, accommodate, very, very simplistic sensory information and very, very simplistic artificial words. When you go to the real, all those assumptions may break down. So with that, let's assume that we have a word model in hand. And what do we do with that? And how can we best use it? Nowadays, maybe this year is the year of agent. I heard, in the AI world, right? So what is an agent? It looks like, your web browser script become an agent because it helps you to browse a couple of websites. It may actually get you a hotel ticket and so forth, right? And there are also reference of an agent as a robot, as an agent doing some daily tasks. And these days, in NSF, I saw a couple of grant proposals talking about the agent for science, doing experiments and so forth. And then, of course, many are calling agent calling different tools, right? Are they really agent? So I don't know. I guess the key focus here is really about automation. I just want to hand it a tool and the resource to some system and they handle it for it. Finishing the job and use some tools. Not sure this really suggests agenthood because when we read philosophy, read psychology, I think agency means something different. And it is that different meaning which drives people crazy. Why we are afraid of, the AI taking the world and destroy us? It's because we are afraid that those AI become agent. They have their mind. They come to us, after us. But if the AI is really just an automation like this, why worry? No, our washing machine is automated. We don't worry that it is doing something bad, right? So in a sense, people are already contradicting, the definition of AI, which caused a lot of safety and psychological concerns. So here, I want to begin by asking, what is really an agent? And then, how to push further. So here, I think here is where we probably start, right? When as a human being, the hallmark of human agency and the human autonomy is we are multitaskable, right? We use our single brain to solve all this. And also we have a goal, driving us, how to, and we can learn, right? And we can continuously learn. We can also, innovate. And of course, we have a free will. I guess, starting from here and here, everyone probably will come with a timestamp. Even if free will can come out of a system, you kind of can imagine it's coming after, many things needs to be accomplished first. It will be maybe decades later, probably not now. But I want to actually get some headway into how we make a more interesting agent. So here is my definition of the agent. It's a model, it's a reasoning model, okay, that generates what I call the purposeful actions and plans. Not just action plans, but purposeful action plans. And also with the complex goals. Okay, it does the following. It can actively perceive information of all kinds. And we know how to do that. We have encoders and decoders to really connect them to our current implementations. It can reason with about purpose actions, meaning that my plan, gets me closer to a goal. It can learn, it can adapt, and also it can generalize across tasks that you learn from a flight control cockpit. Then you can also, go somewhere else to fly the real planes, something like that. And also it can hopefully generalize across platform so that your experience on the World Wide Web can actually enhance your ability to drive cars, to, do games and so on and so forth. Right now, all our little scripts wrapped around the LM called an agent are highly specialized. So I don't really feel, that's the right track, to go forward. So how should we get to what I just mentioned about a more general kind of a purposeful agent? Again, back to this master diagram, I would say the 4 pillars, of such an agent should be, first of all, you should have a way to explicitly, quantitatively define the goal as a goal state. You should have a proper representation of the beliefs, okay, from the real world. You should have a word model which helps you to simulate and, maybe test run and do thought experiment of your plan. And then you, of course, have a planner who can leverage on such a word model to, cleverly simulate all the scenarios, right? So let's focus on what this green box look like. Again, there are existing kind of proposals. I would say they roughly fall into these 2 buckets. One is more like the classical policy-based, approaches. we all know how to do that, right? We have a real world environment. You can kind of do an optimization, directly in the space of action sequences and get there. It's usually very good for fast reaction. So you can see in this diagram, you only have, the states and a pi, the agent. There's no world model, no environment, and so forth. Alternatively, there is a reference to use the world model, as a simulator. But again, it is more in the space of, latent space kind of reconstruction and so forth. But again, it offers the advantage that is not possible over there because it allows you to do some long-term reasoning because of the latent state representation from the world models. And there are some examples, in each of the camp. I'd say that, probably they shouldn't be contradicting each other. We need sometimes this muscle memory fast reaction without even passing our brain to react on something. And sometimes we need to be more thoughtful. If we run a company, run a department, run a university, of course, we need to do a little bit more careful thinking rather than just instinctively think. So I think these two things could go together. The problem is how to do it. Right. So again, I would just maybe dive in by making some remarks about each of the proposal. So this proposal has the deficiency that it is almost like a how should I say, the hardwired system. You train a policy-based model with some fixed data. What if your words gets enlarged? You have a fixed neural network which is very, very difficult to extrapolate. And also, if you are lucky, I give you more computers, I give you more memories. Can you even use that? Well, at least based on current architecture, you have a fixed amount of time needed to compute a policy. You don't actually, you cannot really use the more resources to do flexible, decision making. It's unlike the world model. If I have a bigger memory, more machine, I maybe simulate more steps, right? I want to do more thought experiments. That flexibility is not offered in here. Therefore, we believe, there is a potential to do a mixed decision maker where, you can introduce a configurer which, switch you between the policy-based models and the world model-based models. That's kind of one, proposal. Now, the world model-based proposal only also has some deficiency because, it is, how should I say, very, very, difficult, to train, because, you don't have, the memory and also the explicit representation of the goal to, allow you leverage on past experiences. What if, I have something that, I see before and, I want to just cache out what I already learned. The current, architecture in here doesn't allow that. Again, very simple. You can just keep adding to that components and add long-term memory and, a critique of, goal, accessibility and so forth. Right? So that basically leads to, a new architecture, the PEN agent model, which has all these key components plus the external augmentations that includes, whatever you feel necessary, especially long-term memory and also, maybe even emotion and self-identity and so forth. So I think this is maybe a engineering-wise more plausible, actionable roadmap to build that. And the end outcome is that you have a system which gives you system one and system reasoning. So you can be both reactive, instinctive, but also very deliberate and conscious. Okay, so this is a blow up kind of a zoom in of the model. It's a little bit intimidating, but let me just explain. You started from the world, the universe, right? And you have, maybe the actions which directly encode your states, or just from observation. Then they turn into your observation from here. Your observation is outside of agent. They enter the agent through encoder, turn them into belief. And then the belief will be used by the planner to trigger the world model to start a new sequence of experimentation, because my experiment needs to start from somewhere. I start from here where I stay. Or they can use to pivot existing simulations to see which one is closer to where I am. I'm going to drag it out. Therefore, accordingly, you can suck a action in any step out to become the action of this agent. So it's kind of an intuitive plan that is purely actionable. I can now assign, some characters into that to turn them into a mathematicalizable equations. And the loss function can be defined over there as a reinforcement learning loss. And then here we go. You can train. Okay. And, I think this is a model that is, incrementally, implantable, which is what we do. And, it also has a potential to grow more complex. For example, I talk about the other modules. This is a very interesting module called Configurer, which actually can now, look at your belief states and then make comparisons or make pivoting of your, imaginary simulative states, and then do what is needed to take the best action. There are also sensors and actors, each of them in charge of, embedding the information, or, making, the action proposal based on the states, and the critiques that measures the distances of your current state versus the goal and so forth. Again, they can be all each separately trained in a modular sense and put together. You could also imagine going even further to do more complex planning. Each of these track doesn't have to be a linear sequence. They can be turned into a hierarchical planning. You set up sub-goals and the sub-actions in such a way, and then you have a much richer space, of doing complex plannings. Yeah. So this is roughly the roadmap of what, a complete agent model would look like. And of course, you can even go higher. You can now put two agents together. And the two agents together basically is turning all what I showed in that the hairy box now into this clean box. And then they interact over, a interface where the actions of both actors become the observations of the other agents. And then they basically increase their sensory information and belief, right? And of course, you can get this. So people are talking about having the agent of the world and having all that. It's not easy. Even one agent, you already see such a big panel of diagrams. And now we're talking about two agents and a population of agents and the super agents. But on the other hand, you can simplify, because when you are talking about super agents, for example, a economy, I want to, model the economic behavior of buyers of a house. Well, then I don't need to worry about how you look and where you stay and the other, social behavior. I only care about maybe your particular purchasing behavior. So there is a way to also go reduction and make all these little thing really a white box of highly abstracted kind of representations. Okay, I think I'm getting to the end of my talk. This is what a super agent would like, where, it's a nested structure that one agent become, the subject of another agent, and all agents become just the environment of this particular agent. You can kind of use the same idea, in a nested way to step up, hopefully into the DOM state where you have the super intelligence at some point. All these require, of course, compute and more careful design. So to close up, let's look at what a agent model would simulate in a movie versus a video model would simulate in a movie, right? So this is a pen agent living in the pen world. And just look at this guy. It's not pretty in terms of visual effects, right? But this guy, when he runs maybe on the street of New York, he would bump into, individuals. This guy, he ignored. He bumped into this car. He actually had an engagement with the car in some strange way. And then he would run forward. And you have a sense, maybe he's escaping something, right? Someone is pursuing him. You have it's not an object. It's a real character that has a sensation or maybe a sentiment in that. Right? That's what I mean to be an agent. So when you drive a car, your camera, if it's built on a video generator, then everything else, a person, a car, is an object. It's a cold-blooded object. But if it's an agent, you will actually have now a judgment about whether that car is an object or that car sits your friend and come meet you, or your adversary come to kill you. You actually have very different actions. Okay. You wouldn't just view that as an object. That's actually the subtlety of having an agent model, which actually see the world with a temperature. Okay. With an emotion. And therefore your judgment will be very different based on just a word model or some visual models. So we have some experiment, reducing the whole design now into only the visual language quiz. And we are able to now test the reasoning capability, and therefore we solve some math problems. This is a math problem, not just in language. It has the visual part. Therefore, if you just try them with a pure language model, it wouldn't work. But with the word model that contains images, it is doing pretty decently. This is a rank list of the score. Our model is 7 billion parameters. Okay. And it is actually acting quite comparatively to some models which are 10 times bigger, just because the architecture is a lot more sophisticated. Of course, we have large language models trained in my university, which are tens of billions of parameters. We are hoping that they become the backbone of the larger model we're going to release later this year. Okay, so just to wrap up, I guess this is a agent system that we hope to see down the road. I want to emphasize that these agentic systems are not a system with agency. Okay, these are very, very different meanings. I think nowadays the academic community are abusing these words and sometimes talk about something that is not meant to be, built, by the current engineering efforts. So I just want to make this clarity. Just to conclude, I think time is up, so I'm going to now pass the philosophical debate, because there has been this Kantism and the humanism debate about whether I build a causal model or not. To be honest, especially in my other project looking for foundational biology, I care less about causality. I care about simulating the reality and also predicting the complex phenomenon. Therefore, I think humanism is something that is on the rise these days. It's like when you design a vaccine, in the 18th century, you don't know DNA, protein, anything, but you still use vaccine, even though, you not necessarily know the biology. There is a different way of measuring value, reliability, and quality, other than just like Newton did, knowing the mathematics and compute everything. I think that's what AI is right now doing. We are rolling out a lot of strong functions without knowing how, but I don't think not knowing how is a reason to reject all these new technologies. I think that's what I'm trying to say. And I think what's next is to really place our models and our effort into these larger and larger circles, which is populated with more modalities and more information and more activities. And then from there, you derive the functions, which can in turn, govern the design and the validation of all these models and systems. So future of AI, I don't know. I think you can call them agents word and so on. But I don't think, intelligence is something that is worthy, that kind of a philosophical debate at this point before we see all these functions realized. Just to sum up, I want you to maybe take home with the following messages from this talk. If you want to remember one slide from my talk, that's the one slide, right? So a word model is not a video generator. And a agent model is not just a bunch of scripts wrapping around a LLM to call functions, right? It is a system that understands, predict, and reason toward a goal, and in all sorts of environments. And then I presented our the PEM model, which is architecture for purposeful and general reasoning, and it has the following decision kind of technical design, for data representation, architecture, loss function, training schemes, and the different modules. So with that, I thank you for your patience, and sorry for the very, very long, verbose, very raw presentation, and I'm happy to answer questions.
Well, thank you, Eric. Wow, that was an incredible talk. Seriously, I mean, there's so much packed in there. People are going to spend months thinking about it. So thank you again for preparing the talk for us and coming here. So now I'll open the floor for questions. Yeah.
Thank you, Eric. This is really nice talk. I actually come to this lecture before with a quick question out of genuine curiosity about AI. There are some notable figures. They say the development of AI may pose some threat to human beings. This voice comes from Alan Turing, Geoffrey Hinton, Yuval Harari. I wonder what is your take on this? And combined with this lecture, I wonder, imagine 5 or 10 years from now that AI is embodied or even weaponized and incorporated with a word model. I'm concerned about two things. One is how do we prevent bad people use this more powerful AI from doing the bad things, how to prevent malicious usage, because we already see some people using current AI generate pornography or synthesize audio. And another is how to, implement some safeguard to make sure that AI serve for people, not to serve for themselves, and prioritize themselves over human beings. Thank you.
Yeah, thank you for the question. It's not a technical question, but I'm happy to share some thoughts. Right. What you are asking is really a question for the people, not a question for the technology. Technology always advance and solve problems and offer functions and so forth. But people can make bad use of that, and that's why we have a legal society that has laws and have all these litigations and vetting of this. I would say treat AI as a product and legislate proper regulations and the laws around it, right? But here you can see that the law and the legislation and regulation are around the product of AI, not the science of AI. I think once this is clear, I'm optimistic that on the one hand, you can continue to advance the science of AI and having more and more powerful models out of it. But on the other hand, there can be mature legislations and regulations to prevent the abusive usage of AI. I think this is very, very important to distinguish. You abuse a tool doesn't mean the tool is bad, right? It's the people that you need to, put it. For example, right now, I don't hear too many people are talking about, hey, we have fake news and we have pornography and so forth. What's the punishment for people doing that? We talk about what's the punishment of a company of the inventor who made that happen. No, I'm not, with that kind of thinking. I think there are ways, in fact, to trace every production of every digital content if you want to. It's just like whether you want to or not. You have a digital watermark of everything you can simulate if you mandate it. And you can also make it a mandate by saying that if you don't do that, I throw you into jail. This is doable. It's just a will of the legislators and the will of the people, not the technology.
So I'll ask you a somewhat technical question.
Yeah.
So, you talk about the ability to simulate. I think that's extremely important for the next level of capabilities. Now, I think most of these LLMs, they're very, very powerful, very capable, but they're kind of in the Shannon world of entropy. For instance, the entropy of pi is infinite, but the Kolmogorov complexity of pi is very small, very finite. So does the PAN architecture let you translate between or transform between the Shannon world to the Kolmogorov world to understand a pattern and, simulate it?
Wow. That's a very, very profound question. I need to first dive deeper into exactly what is a Shannon complexity and what is a Kolmogorov complexity. If I may guess,
well, let me put it another way. To memorize pi, you need an infinite amount of bits.
Mm-hmm.
But to simulate pi, you need a very small program.
Yeah, that's
right?
the point. Yes.
So LLMs are kind of in the first world memorizing.
Yeah.
Yeah.
So I don't think LLM is actually just memorizing. Yeah, it memorized a lot, but actually it simulates even more. That's actually exactly a point we can discuss. Is LLM just a deterministic next word generator, or it is actually a simulator of linguistic activities? I took the later view. I think it is literally a simulator of what a human would communicate with you verbally. And that's how I take it. In a sense, the LLM can give you surprises sometimes, and they can hallucinate, for example. And the hallucination itself is naturally not the product of a memorization. It's actually simulating, right? And it's just simulating not up to your standard or maybe to your surprise. So in that sense, I think LLMs and the word models and even these agent models intrinsically are not different. They are basically building their internal world from data, but they actually extrapolate, from that data. In a sense, their capability is beyond, what the data, they use to train, to define them. That's kind of my guess. All right.
Thank you, Eric. Thanks again for
Thank
the
you very
wonderful
much.
talk, and thank you for coming.
Thank you.